and welcome to Dr. G's Technique of the Week, Precalculus Edition.
Today we're going to be looking at two important theorems, the Reminder Theorem and the Factor Theorem, and seeing how we can apply them in some useful ways for polynomial. So we're going to start with the Remainder Theorem. The Remainder Theorem tells us that if we take a polynomial f of x and we divide it by a term x minus c, where c is just any number, the remainder after performing that division is equal to f evaluated at the number c. So let's consider some examples. First, we'll let f of x be x to the fourth plus x cubed minus 6x squared minus 5x minus 15. And we want to find f of 5. So first, take a moment, try this we'll call it the old-fashioned way without using the remainder theorem. Put in 5 for each place that we see x. See what you get for f of 5. Now let's do that same calculation, but the new and improved way using the remainder theorem. So to divide f of x by x minus 5, since 5 is where we want to evaluate our polynomial, we're just going to set up synthetic division, which in terms of the actual calculations is a pretty simple and straightforward process. So we set up our 5 to divide in, and then we take our coefficients in order from f of x. So 1 x to the fourth, 1 x cubed, negative 6x squared, negative 5x, and negative 15. Pull down our 1. 1 times 5 gives us 5. 1 plus 5 is 6. 6 times 5 gives us 30. 30 plus negative 6 is 24. 24 times 5 is 120. 120 plus negative 5 is 115. 5 times 115 is 575. And 575 plus negative 15 is 560. So here's our remainder after dividing our full degree 4 polynomial by x minus 5. This tells us that f of 5 is equal to 560. So hopefully that's the same thing that you got when you just plugged in 5 into f of x and evaluated it, but this definitely is a lot faster, takes a lot less arithmetic to make happen. This also makes it easier to deal with complex numbers. So for example, if we consider g of x, which is equal to x cubed plus x plus 10, suppose we want to see if c, which is equal to 1 plus 2i, so a complex number, not a real number, if this is a 0 of that polynomial. That would imply that g of c, so g of 1 plus 2i, is equal to 0. So that's the question that we want to ask. And we can evaluate g at 1 plus 2i using synthetic division in the remainder theorem, which is a lot easier than having to raise 1 plus 2i to the third power. So we just simply take that 1 plus 2i, put it in our box, pull our coefficients from the terms in g of x, so 1x cubed, 0x squared, 1x, and 10. Pull our 1 down. 1 times 1 plus 2i is 1 plus 2i. Plus 0 is just 1 plus 2i. Now we have to do 1 plus 2i times 1 plus 2i. Take a moment, work this out on your papers now. Don't forget to distribute. So you should have 4 products to add together to get your simplified answer. So 1 plus 2i times 1 plus 2i is negative 3 plus 4i. And 1 plus negative 3 plus 4i gives us negative 2 plus 4i. Now if we multiply 1 plus 2i times negative 2 plus 4i, it's simplified to negative 10. So our remainder is 0, and that tells us that in fact, g of 1 plus 2i is equal to 0. So we have this complex 0 or complex root of the polynomial g of x. This leads us into the factor theorem, which is a special application of the remainder theorem. Since factors of polynomials and their roots or zeros are very closely related, we'll be able to determine if something is a factor using a really similar method. The factor theorem states that if we have a polynomial f of x, that f of c, just some number c, is equal to 0 if and only if x minus c is a factor of f. Which makes sense using the remainder theorem. If we divide f of x by x minus c, and we get 0 as a remainder, that means that x minus c was in fact a factor. And that 0 remainder by the remainder theorem is equal to f of c. So for example, with our same polynomial g of x, since g of 1 plus 2i was equal to 0, that tells us that x minus 1 plus 2i is actually a factor of g of x. So we can even use this as a way to help us find complex factors of polynomials. Now it's time for you to get some practice with these new ideas. See you next time on Dr. G's Technique of the Week.